So yesterday we said that we have a list, which is simply a collection of arbitrary objects. We can refer to a place in that list by using an index. It's convenient for retrieval and replacement. If we use an underlying array, we can easily index into that list and then replace or retrieve an object at a particular index. We can also do constant time insertions and removals at the end of our list. If we use that underlying array in circular fashion, we can then also do constant time insertions and removals at the beginning of our list. All right, we did see that if we do arbitrary inserts and removals within our list, then we will have to shift all the elements that occur after the ith one that we're trying to remove or add. And so we can have to move up to n elements shifted either to the left or to the right. So as a replacement, so if we're to use our adapter pattern to use a list as a queue or a stack, then an array list works very well because we can do constant time insertions at the beginning or the end. That allows us to do a queue that has constant time operations, or simply doing operations at the end, we can create a stack that has constant time operations. So it's useful. Initially, its one limitation was that if we're using an array, then arrays are fixed size, so we have this fixed capacity, which means that we have to know beforehand how many elements we're actually going to be working with, which we can't always do. So we want to get around that. We introduce the concept of growable arrays. So we have this growable array-based array list. And in that case, what we'll do is each time that we want to add something to our array list, we first check, when I add this thing to my array list, is my array going to be full? So that's that first line, the line 2 there. So if n is equal to s.length minus 1, so if I'm actually going to add it to the last index, then what I should actually do is create a whole new array of some size. I'm then going to copy everything from my old array to my new array, and then I'm going to chuck away the old array by making the old array an alias, or the variable that was referring to the old array, an alias to the new array. All right, then we actually go ahead and add that new element to our array. All right, then we discuss that we have two different options when it comes to how we're going to grow this array. We're either going to add a constant amount of additional space, or we're going to double each time. For that adding a constant amount of additional space, I'll answer questions regarding the practice at the end of the lecture. All right, we're still discussing theory here. So we know that we will have to actually do n inserts. That first n refers to the inserts that we're going to insert, the n elements that we're going to insert into our current array. Granted, that current array is going to be swapped out for a larger one several times, but each new element will at some point be inserted into the current array. So that's what that n represents. The next term, if we start out with an array of size c, each time adding c more spaces in our array, then the first time we swap out our array for a larger array, we will copy those c elements into the new array and replace it, that new array of size 2c. Then when that array has been used up, we'll swap it out for one of size 3c, so we're adding c each time, and that means copying all those 2c into the new one. So that's where that 2c comes from. We're going to do this k times, because k is simply n divided by c. So how many c's we need to do this? You may say, okay, that last one isn't actually necessary because we're only adding that nth element. However, remember when we're about to add that nth element that fills up our array, we're going to create a new array. Right? Then copy all n of those into that new array. We'll now have an array of size n plus c that will still have some space now for new elements. So that's how each of those terms comes about. We see that all but the first term has a factor of c. We factorize out that c. We now have a series that we're quite familiar with. We're adding from 1 to k. We already said that if we add that series to itself, we end up with k terms, each equal to k plus 1. That gives us that little multiplication that we have there, c multiplied by k plus 1. Because we added the series to itself, we divide by 2, and that works out. If we then substitute k is equal to n over c back into this, we'll end up with 2 terms still. The one term is simply n, that's a linear term. The next term is n over c multiplied by n over c plus 1. Yes, there is a c outside, it'll cancel out a c, but regardless, we will end up with some n squared term. We said that in big O notation, that will simply give us on squared. All right, so I trust in your review of yesterday's work and this discussion, we're now convinced about how we come up with this sum over here, that we are used to calculating this series now. We discussed it a couple of times. And from that, we can substitute the value of that sum and then substitute back our k is equal to n over c. And we end up with a quadratic equation, rather a quadratic expression. And that in big O notation is simply on squared. Right, that, remember, was Tn. So that tells us how many operations have to be done to be able to insert n elements. That tells us that on average, the time taken for a single insert will then be Tn divided by n. All right, so this whole thing here was Tn. If we divide that by n, then we end up with something that is order n. That is linear time. Point. Then, what if instead now, we already discussed that, what if instead now we double it each time instead of adding a constant amount of new spaces? Well, in that case, let's start out with one of simply capacity 1. Then, when we're actually about to add something to that, we say it's going to be full, so we create one of capacity 2, double what we had. We then insert that 1 into that one of capacity 2. Then when we want to add another one, we see, oh, it's going to be full. We have to double the capacity and then copy over those 2. So then we're copying 2 to the next one of capacity 4, and we do that each time. Note, we're going to do n inserts because we are actually going to insert all n of them into the current array. Granted, sometimes we will be swapping out that for a larger one. And for each time we swap out our current one for a larger one, we'll first copy 1 element. And the next time, when it's about to be full, we're going to copy 2 elements over to the new array, then 4 elements over to the new array when that one's going to be full, then 8 elements, and so on. We do this how many times? Well, we'll have to do this number of times that we have to double from 1 up to some number that we can now fit in n elements. We said that the number of times that we can divide n by 2 is simply log base 2 of n. And so if we solve for n in that, we end up with 2k, right? This expression here, solve for n, we get 2 to the power k. If k is equal to log base 2n, then that means n is equal to 2 to the power k. All right, so that's how we end up with this. That will be the last number of elements that we copy over, which is simply n. Then, well, this new series, this new sum, we discussed yesterday that this is actually equivalent to a binary number with k ones. All right, there are k of these. And if we were to add 1 to this, we'll get all these overflows, all these will become zeros, and we get a 1 in the next digit over. So that's now 1, 0, 0, 0. There are now k zeros. Well, this is simply the number 2 to the power k plus 1. We had added 1 initially, so we'll subtract 1 from that. Right, you'll see in the very next line, that whole series is replaced by 2 to the power k plus 1 minus 1. Great. Now, how do we get from that to 3n? Well, 3n minus 1. Well, the 1n is over here. That was still there. The negative 1, that was there as well. So this 2 to the power k plus 1 should be equal to 2n. How do we get to that? Well, if we take this first sum, or this first equation we have here, where k is equal to log base 2n, and we want to find out what 2 to the power k plus 1 is. So we're first going to add 1 to each side, which certainly remember an equation stays true if we do it to one side or we do it to the other, unless, of course, that's for inequalities. Yes, so as long as we do it to one side or we do it to the other, then it holds true. All right, then we will raise each of those as powers of 2. Okay, as long as the bases are positive numbers, then this stays true as well. Log base 2, I think come out very nicely, plus 1. All right, now on the right here, you should remember this log rule, that 2 to the power log base 2n should actually then give us n. Why? Because the question, log base 2n, is how many times you have to raise 2, to what power do you have to raise 2 to get n? If I then raise 2 to that power, I of course end up with n. However, I don't just have that power, I have 2 to that power plus 1. And so remember, we're simply adding exponents when we multiply numbers with the same base. So that's the same as 2 to the power log base 2n times 2. That simply gives me n times 2, which is 2n. All right, that's how we get to 3n minus 1. It's n plus 2n minus 1. That gives us 3n minus 1. All of this is equal to tn. So the number of operations to insert n elements will be 3n minus 1. In big O notation, that is order n, it's linear time, right? But actually, we're not interested in tn. We want to know how long it takes to insert a single element on average. And so we divide tn by n. That gives us n minus 1 over n. In any case, that's some linear function, and that is simply order n. All right, sorry, no, my goodness, that should be order 1. It was order n, we divided by n, that's order 1. So what we've seen here is that if we're adding a constant number of cells when we increase the size of our array, then on average, a single insert will be linear time. If we are doubling our array each time, so the doubling strategy, then on average, a single insert is constant time. Granted, they won't all be constant time. Sometimes we're copying things over. But on average, when you count them all together and then divide by the number of insertions, on average, it's constant time. So when faced with this question of whether we want to follow this constant, the strategy where we're adding a constant amount of additional cells, or the strategy where we're actually doubling the size of our array each time, we'll rather follow the strategy of doubling our array each time, right? Because it's 1 order of magnitude faster. It's constant time on average, whereas the other one is linear time on average. All right, so I trust we understand that. If there are questions, then please do ask them. Is this proof or calculation examinable? Well, certainly. Now that you guys are doing open book assessments, this is certainly within your capability because you've all done logarithms and equations and so on and so forth in high school, and we've actually now reminded ourselves how this would be done. Right. All right, so that's just what we ended up with. This geometric series where we're going from 1 and then doubling that to 2 and then doubling that to 4 and then doubling that to 8 actually comes up in our discussion of trees as well and a couple other places. So make sure that you understand it, that we can simply represent that as a binary number and then add 1 to that to get the simplified expression to be able to count these things up. So just note that it will come up again. All right, but our idea is that we were counting up all of these to get Tn. Tn is order n. So that tells us that on average, a single one is order 1. All right, there is a proof of this or the same type of calculation within the text. All right, so our array list interface would look like this. As I said, it's also called an index list because it's a list with the idea of an index introduced. We now refer to any place within our list using an index. That allows us to be able to easily access and modify things within our list, and also do constant time additions and removals at the beginning and end. And so it's useful if we want to implement a stack or a queue or some less general list using that adapter pattern. So it's useful. Right, if there are any questions, because we're the end of our discussion about array list, we now continue our discussion with a different kind of list, where instead of using indices, we now use positions. So if there are any questions, please type them in. We still have time to repeat anything, so we're all on the same page. All right, while perhaps people are jotting questions down, I'll remind you we discussed the idea of a position. Right. A question again about the prac. As I've said in class yesterday, the prac is going to be on either stacks or queues. They're pretty similar. You should understand both, and you can be asked to implement one and work with it. We're going to work with these next week. All right, so this won't be this week's prac. However, you do have to understand this. You may not be thinking about it right now, but 2 weeks from now, you'll be writing a semester test. And of course, this will be in that test. So the position ADT, if we remind ourselves, it has a single method element which simply returns the element stored within that position. Positions, unlike indices, are relative. So it doesn't refer to a place in a list by this absolute index that tells you how many elements appear before it. It simply allows you to be able to access what is stored within that position, but it also has some order. A list of positions will also have some order, but we can simply access what comes before and after a position, but it doesn't tell us anything about that position's place within the entire list. Right. And so if the element stored at that position changes, the position itself does not change, right? Its order within the list does not change. And if elements are removed before or after this position in the list, that position again does not change, right? Because it doesn't use an index to retrieve the element stored at that position. Even though we do understand that by definition of an index, if a position is removed before that one, then the number of elements stored in the list before this have changed, so the index has changed. But if we use positions rather to refer to place rather than indices, then the position itself does not change. The only way it would change is if we actually remove the element that it stores from the list, thereby destroying that position. Otherwise, it does not change regardless of what's going on around it, or even if its particular element is changed. Right. And so we can say that a list contains an element E that we want to keep track of. Previously in an array list, we would have done that by keeping track of this index. However, that changes depending on insertions and removals. If instead we use a position that's associated with an element, it allows us to access that element and to keep track of that element stored within P, regardless of changes around it, regardless of changes of the index of that element within our list. Right? If you have a reference to P, you can always access E, regardless of whether or not the index has changed. However, in our index list, we use that index to index into the underlying array. And so we're actually using index to keep track of an element. If things change around it, in particular before it in the list, then we have to update that index to keep that reference to that same element. But with positions, we don't have to do that. All right. Yes, the position ADT is associated with the data container. That comes down to the actual implementation that we do to realize that position. But as an abstract idea, as an ADT, it simply has a single method element which will return to us the element stored within that position, and we can keep track of that element regardless of whether or not the index changes, as in the number of elements before it change within that list. So it's convenient for that. And so this leads us to the idea of a positional list. So a list where we use positions to keep track of elements. We use positions to refer to a place in a list rather than an index. You may think, well, we've used something similar to this. We've used our city linked list and our W linked list. Well, that was specific concrete ADTs. In this case, we want to talk about, concrete implementations of data structures. In this case, we want to talk about the abstract ADT of positional list, regardless of how we're actually going to implement that position. When I talk about the idea of using position to refer to a place in a list and storing an element within each position. So it allows us to refer to place without index. If we happen to be using a linked list, then we could use the node to implement our position. Right? We could if we were using a linked list. We're not restricted to that though. If we were to instead use index to refer to place in a list and still use a linked list as our underlying data structure, it really would not be convenient because anytime we actually want to access an element at a particular index, we have to begin from the beginning of our list and link hop all the way, keeping account until we get to the index that we want. That is not great. Right? In worst case, that's linear time. That's not really something we want. It certainly isn't convenient. And that's simply to access a particular, so if we want to retrieve an element at a particular index, or we want to change the element at a particular index, or even to remove it, we would need to do this link hopping if we're referring to the place just within the index. If, however, instead we use position to refer to a place in the list, then it becomes really easy. As long as you have a reference to that position, we can retrieve in constant time, simply call that method element, and we can actually do arbitrary inserts and removals, as we will see. All right, I believe there was a question there that actually had to do with theory. So we can think of it somewhat like a random access linked list. Okay, by random access, you mean that we can actually in constant time access any point in that, like random access memory, then yes, it's exactly like that. However, we'll see that there are some caveats, right? If we weren't using a linked list, or as we've kind of discussed before, if we're using single linked lists, then certain methods like add before wouldn't be constant time. So not all the operations will necessarily be constant time, but certainly accessing will be like random access. All right. So if we're talking about a positional list, having a node means that we can perform constant time insertions and removals as this node accesses the position which stores the element. All right, another question. When you access a position, does that also mean accessing the reference? Right, well, to be able to access the position, we have to have a reference to it. So we have to have some way of referring to it. You'll see that all of our methods refer to positions, not nodes this time, but positions. But that means that you have to have a reference to a position to be able to do some operation on it. Similar to the ideas of a linked list, and this, much like how the array list is an abstraction of the idea of an array, a positional list is an abstraction of the idea of a linked list. But we'll see that by using this abstract idea of a position, we can actually then abstract away the inner workings of our nodes, which is advantageous to us because that means that we don't have to rely on a particular implementation for our nodes, and also we don't allow access to nodes for any users of our positional list, which is a good advantage. All right, but yes, we do have to have a reference to it. Right, we then have add before v and add after v, where v is a node, right, if we're using a linked list. However, we don't want to do this. We don't want to directly access our nodes because that could then give access to all the attributes of our nodes, including their references. And so if one were to change those references or set them to null, it destroys our entire list. Right? Everything off that node can't then be accessed. So that's not good. Instead, if we only expose the position, which remember has a single method element, it allows us to retrieve values. However, we aren't able to change anything within that position, or within the underlying node, like destroying links within our list. Right, so exposing a node exposes too much information, whereas if we simply expose a position, that does not expose that. And so for our positional list, all our operations will refer to positions, not nodes. So now you'll see first and last, right? Those will return positions storing the first and last element in our list. Previous P and next P refer to positions, not nodes. So previous P will return to your reference to the position before this position P, but you're not able to change the next reference of that position to destroy the list. Similarly, you can get a reference to the position that occurs after P in this list, but it only allows you to access the element stored at that particular position. All right, we still have our update methods, but they too refer to positions rather than nodes. Set PE would then set the element stored at the position P to E, would usually return the old element. However, this does not change P, simply now is storing and keeping track of a different E, but its place within our list is the same. We can still refer to it and get that E that it now stores. Add first E would create a new position and add that to the beginning of our list. Add last E would create a new position and add that position to the end of our list. Add before PE would simply create a new position, insert that before P, and store E within that. All right, but if we actually have a method add before PE, then that means that add first and add last are actually redundant. We could just say add before first and E, pass E as well. That would add something at the beginning of our list. Similarly, add last, we could simply add before our sentinel node or add after our last node. Would be able to add something without having this a separate add last method. All right, but are there instances where we could be throwing exceptions? Are there instances where our methods should throw some kind of error because something has gone wrong? Well, certainly, if we try to do an operation on a position that isn't a valid position, as in it's not actually within our list, then we should throw an error for that, because the thing that you have passed us, the reference you have passed us, isn't actually a position within our list, so that simply will not work. All right, this positional list is now another data type that we could use to implement DEX, our double-sided queue. So because we can add first, add last, and also remove things arbitrarily, so we could remove what's in the first position and what's in the last position, we could easily expose just those methods to create a double-sided queue. Would simply have a private instance of our positional list and call those existing methods within our positional list to implement the methods add front, remove from front, add last, remove from last, or add rear, remove from rear that are within our double-sided queue, also known as a deck. All right, if we were to implement our positional list using a doubly linked list, then that'll be really convenient because we know that all our operations will be constant time. In this case, then, our D node, so the node that we use for a doubly linked list, would implement the position interface. Note then that in all our methods, because our methods actually refer to positions and not D nodes, then when we want to or when we have to make changes to the attributes of the underlying node, like when we're doing an insert before and insert after, we would have to then cast our parameter, which will be of type position, to the underlying D node object, so cast it to that, and then be able to access those attributes of the D node. However, that doesn't mean, so we can do that within our implementation of our positional list that we implement using this doubly linked list. However, outside of that, whoever uses our positional list would only see the positions within it and would not then be able to access the underlying nodes and make changes to our list. And that we don't want, because then whatever they do will depend on the particular implementation of that position. So if we change how we implement that position, their code may not work. And also, they could do things within their code that could destroy our list. So we don't want either of those things to happen. Right. So I trust we see why this would be a useful ADG. Firstly, it allows us to refer to places in the list without using an index. And so we won't have to update indices to keep track of the same element. We now have this relative idea of our place where the P, the position itself, doesn't change if the element changes, or if any positions before it are destroyed or others are added. by using a position, we only expose that single method element. And so we can implement this list by having some concrete data structure like a W-linked list, which uses these D nodes to implement this list. But those D nodes will themselves implement position and only expose that single position method. All right. And we have a question. Is this lecture slide the final thing we'll find in the semester test? No, certainly not. We're not going to stop 2 weeks before the semester test. So positional list ADTs mainly store the position of an element regardless of its value. What are some use cases for the positional ADTs? All right. So as I said before, we can use it to, okay, like a general list, we can use it to implement any less general linear ordered data structure. So our stack, our queue, our double-ended queue. If we have this single, if we have a single implementation of our positional list, then we can implement any of those. The position ADT itself, so position or positional, that one then encapsulates some concrete implementation and allows us to refer to place without referring to something like an index, but also to only expose what's stored within a position. All right. And certainly we will ask you after you've implemented this to use the adapter pattern to implement the things that you've worked with before, like stacks, queues, and decks. All right, I don't think you have any other questions coming in, so go ahead, but you can still add questions there. And time aligned, we will address them. All right, so I'll add after PE. This one actually uses position or refers to a position. We would create a new node that would work with this, very similar to how we did with our W-linked list. We have to change two references, the reference of P to now point to this new node. You see that's the very last line there, set P.set next must now refer to V. We have to then change the previous reference of P's next to now refer to this new node. That's line 6. So P.get next, that returns to us the next position. It's.set previous to V. And we're setting what? Okay, so the current one that we are creating, we set its element to P, we set its previous, so we set its element to E, it's previous to P, and it's next to P's.next. Granted, this is really simply at pseudocode level. If we're actually doing this and working with positions, remember, we would have to cast to a node before we do any operations that work with the underlying data structure, like changing references. All right. So we can choose this or other ADTs to implement stacks, queues, etc. Positional is just better. Yes, we can choose, though oftentimes if we are asking you to answer a particular question, we will say, all right, here's an implementation of a particular data structure, or assume that you have one that implements a particular ADT. Now use your knowledge of that ADT to create a new ADT using the adapter pattern. So we could, give you a UML or simply the interface that it implements, so that you know exactly these are the methods that it implements. Now, knowing what you have to implement, you can then call those methods. We'll first create an instance of the type that implements that interface, then create the new type by calling methods of that particular instance that you've created. All right, so you can easily do that if you know what you're trying to do, and certainly we expect that you know what all the behaviors of a stack, a queue, a deck are. All right, for the stack, you can simply access things at the top, so you can do push, pop, and top. For our queue, remember, you can add things at the end, and you can remove things from the front, and the deck, you can add and move from both ends. That is certainly not asking too much. All right, so there's one more idea I want to discuss before we talk about sequences, and that is the idea of an iterator. You use these a lot, so you should have come across the idea itself, but we want to talk about the iterator ADT and how do we make the data structures that we've already talked about iterable. So how do we create iterators over them to be able to traverse all the elements stored within any of our ADTs? And in fact, even ones that we're going to continue to discuss afterwards, we'll often discuss, well, okay, this one may not have a linear ordering. How could we create an iterator over this to be able to return this new data type that one could use to traverse, to go over all the elements that are stored within this data structure? Right, so an iterator abstracts the idea of scanning through a collection of elements. It allows us to access and make changes to the one that we're currently at, and then also go to the next one. So we can scan through everything that's contained, all the elements contained within some data structure. It is independent of whatever data structure it's actually iterator over. We'll see that we actually have to create a new type and return that as our iterator. All right, so it should be independent of any specific implementation of the collection that's actually created over. Just note that that second point, that we can access and also make changes, isn't true in the case of Java. For Java iterators, you can't actually make changes, but you can access the current element that you're looking at and go on to the next one as well. And that's simply a property of Java iterators, but we'll look at that. So the iterator ADT should have the methods has, next, and next. Has, next allow us to check, well, are we at the end of our traversal? Is there still a next element? So as long as there is one or more elements still remaining after the current one, then has, next should return to us true, that there is a next. If, however, we're at the last element in this traversal, so the last element in this scanning of the elements of this data structure, then it should return false. And so that allows us to be able to iterate through it nicely. All right, and then next actually allows us to jump to that next one. Logically, we should check that there's a next before calling next, because if there isn't, then we'll get an error. So it extends the concept of a position. We said position already allows us to access an element at a position. If we now add the ability to move on to the next position, and also check, is there a next position, then that gives us an iterator. And we usually implement these using an array or a single linked list, right? Why not a W linked list? Well, we want to do a single traversal over the elements of whatever collection we have defined this iterator over. So we simply need to move in one direction from the beginning of our traversal to the end of it. So a single linked list is just what we need. A W linked list will be simply storing references to previous elements that we'll never use. So an iterator is typically associated with another data structure. As I said, we usually define an iterator over another data structure. So we'll have, let's say, for example, a list. If you were to try and take the list as we've defined it and call a method which requires it to be iterable, like for each, then it would not work. We have to actually say, this is how we actually have to define a method that returns an iterator over that list, and that will allow us to use it in such methods. So we're asked, how is the iterator and position ADT connected? I would not say that they're connected. It's simply that the iterator has what the position ADT has and some extra. It can retrieve an element, so it has that element method, but it can also check, is there a next position? So it's something that occurs after where we're currently at in this traversal, and let's move on then to that next one by calling next. So it has more operations than position. So it's one way of thinking of an iterator, as we take a position and we add some additional behaviors to that. All right, so an iterator is typically associated with another data structure which can implement the iterable ADT. So note, iterable means that the ADT that we say is iterable has a method iterator, which will return an iterator over the elements of that ADT. So the iterator is the thing that we actually use to traverse the elements of the ADT. If this ADT has an iterator method, then we say that it's iterable. All right, in Java, we'd say that it implements iterable, and so it has to have an implementation for the method iterator. All right, so just know that those are two related but slightly different concepts. Which implementation is better, array versus single linked list? All right, well, an array stores less than a single linked list, right? Well, actually, well, that is assuming a lot. Assuming that we have a fixed size or number of elements that we're going to be working with, then the array would store as much space as we need to be able to store those n elements, where the linked list would create space for those n elements and also an additional reference to each next one. However, if we don't know the size, then obviously the array is not useful. All right, but since we're usually creating an iterator at a particular moment in time, and that's exactly what Java does, it creates a snapshot, then if anything changes in the data structure, we don't want those changes to be propagated into the iterator, and so the array is a nice quick way to do it. The linked list will work just as well. Okay, a single linked list will have what we need as well. So we can change the ADTs that we looked at thus far: stack, queue, index, list, and list. And even the sequence ADT that we're about to discuss, we can change any of these to make them iterable. All that demands is that we should create a new method called iterator that will return to us an iterator of whatever type if we're using our generics framework, which we should. And then we can say that this particular class then extends iterable because it has the method iterator. All right. So there are two types or notions of an iterator: a snapshot one, which freezes the data structure at some moment in time. So when you call iterator, it will give you an iterator over the elements of that data structure at that moment in time. If anything changes in the data structure, those changes will not happen to the iterator. So if you add things to the data structure, let's say we're working with a queue, you call iterator, so you create an iterator over that queue, you start doing some work with it, then you change the queue, so perhaps you remove something from the front, you add something to the end. That new or one less element will not be accounted for in your iterator because it was a snapshot iterator. Whereas dynamic one follows the changes of the data structure. So for a dynamic one, we'd want to use a linked list rather than an array, because then we're always just calling what's the next position in our data structure, so we'd still be able to keep track of any changes. However, Java does not account for that. And so in Java, if anything changes in the data structure that we create an iterator over, then the iterator will fail. Right? It will stop working because there has been some change in the data structure that it is an iterator over. So we call an iterator over this list. Let's say we create an array, copy all the elements that were in our list into that array. If we make any changes in the list, then that iterator, that array, will stop working. All right, someone makes a comment, the only thing I'm doing here is that EJ is consistent with the orange and whatever. All right. So if you work with a fixed size array with a better option. I'm certainly not saying that working with the array is a better option. If we're working in Java, which only allows us to use snapshot iterators, then yes, the array would be the go-to. All right, but we could certainly ask you to deal with a linked list rather. I wouldn't say the linked list is slower, right? There's nothing to say, and remember, even in Java, yes, our code may be the same, but what that code is compiled into to be able to actually be executed on a particular JVM is different depending on our platform. So indexing into a list, or rather indexing to an array, may take more or less time than a link hop, going to the next position that is referred to by the current one. All right. So rather than going forward, the student who said that they didn't understand, which part of it did not understand? Have you used the for each loop before? Let me ask that. All right, please just type the answer. Have you used the for each loop before? If you have, then you'll notice that for the for each loop, you don't create an index and then use that index to somehow, and in fact, let's not even say index, some counter and use that counter to somehow move over your data structure. Perhaps you created that counter with an upper bound of the size of your particular data structure. And so that's one way that you can manually do it. Instead of the for each, you simply say, I have some data structure. I'm going to create something that can store elements of that data structure. And then within your for each loop, you can simply work with all the elements that are stored within that data structure. How does that work? Well, when you create that for each loop and say, this is the element type and this is the data structure, it doesn't actually use that data structure. Instead, it calls a method. That data structure has to be iterable, which means it has to have an iterator method. It calls the iterator method that returns to it an array or a linked list with all the elements of that data structure. That then allows you to very simply move through that array or linked list, and for each iteration, go to the next one and the next one and the next one until there are no next. All right, so I hope that that explains why we would have it. And in fact, it came from the need or the desire to use a for each loop. So we have this idea of an iterator exactly for that. Would we use an iterator over an array list ADT? Because I think of an array is already iterable by default, or am I wrong? Is that true in Java? Are your arrays iterable? Yes, I believe they are. However, remember that if you're using an array list, does that array list have any method? Actually, no, I don't think the array is iterable. Anyway, does that array list have any method that returns to you its underlying array? No, it does not. And in fact, the array list does not necessarily have to be implemented using an array. It could have been implemented using a linked list. We simply said that that isn't convenient because if we're referring to places by index, then you'd have to link hop to get to a particular place. All right. Question, when will we get a review or response to project proposals? Next Monday. All right. The university, we call it an SLA. For feedback and anything is 2 weeks, but for the academy, it's a week. All right. Then is a snapshot a picture of the data at a particular reference? I would say it's a picture of data at a particular time. So at the instance that you call that iterable method, it returns to you, or rather that iterator method, it returns to you that iterator with the elements at that point in time. Right, if they then change, it would stop working, at least in Java. So an array list implemented with an array, these names are going to confuse me. Right, is it implemented with an array? It does not have to be. And if you're asking if the Java array list is implemented using an array, well, we're not talking about the Java array list. I've even said that that's actually closer to a sequence we'll discuss after iterators. But an array list, as in an array-based list, well, because the concept is an abstraction of an array, then it makes sense. It is easiest and most straightforward to implement it using an array. All right. However, we note that there are some methods, as in arbitrary inserts and removals within the array list, that are then not going to be constant time if we implement it using an array. So the array list is very useful if we're simply going to be accessing things randomly. However, insertions and removals will keep to only doing those at the front, at the end of this array list. So that means it works well for using it to implement a stack, a queue, a deck. All right, if they're confusing you, then a nice way to prepare for the test is to, for each data structure, draw yourself a little UML diagram with the behavior of each of those. That is another way of expressing a data type, right? You can use UML to do that. We use interfaces because then we can use them in Java to enforce certain methods, but for your own understanding, you can certainly use any other type of thing like a diagram, because although we speak verbally, we remember things visually. That may help you to understand. All right, what chapters will semester test 1 be based on? It depends on where we get to next week. All right, but I'm assuming that at this rate, we will cover chapter 6 as well. So trees will be, so up to trees will likely be in semester test 1. All right, we're already over time. It's actually the beginning of the next period, so we'll stop there. If there are any other questions, please don't just get rid of them. Make note of them. Tomorrow, before I start the practical lecture, I will ask again. Obviously, as you take time mulling over and perhaps getting a deeper understanding of it, more questions may occur. Please, while we have the time, ask those questions to make sure you understand this, certainly before we move on to the next one. Question, are you going to share a past paper, the past paper? All right, if you wish, we can share last year's semester test 1, although there's a big caveat. It will not be as similar to this one as usual because last year semester test 1 was written before we had this global pandemic, at least in South Africa. It was before we shut down the universities. So that was done in person as a closed book test, whereas semester test 2 was an open book test. And of course, this year, your semester test 1 is going to be done remotely. And so you will have access to the text. Certainly, you're not allowed to access any online sources. And we do a search to make sure that you haven't done that and a comparison score. However, just note that it will be different. All right. All right, so thank you very much. We'll stop the recording there.